Press the bell icon on the YouTube app and never miss another update.
Here and then dear students, for today's discussion I'm going to have it laws of motion, and in different sessions I'm going to have the complete discussion related to the laws of motion as one part, and and few more sessions related to the friction as few more parts I'm going to have the discussion. So firstly, with laws of motion, the major things about Newton's laws, the first thing, and their illustrations, and mainly about the Newton's second law and third law applications and illustrations. We need to have the discussion in depth about all those. After that, and then drawing the free body diagrams and solving for the problems in dynamics. Accelerated bodies, how we have to solve the problems, like involvement of tension in the string and so on, so things. How to, by drawing the free body diagrams, how to solve the problem. That is a major task in dynamics, what we have to solve it. We'll have the discussion. And again, on the other part of it, friction, I told you, as different parts, friction on horizontal surface, friction on vertical surface, and the problems related to that, particularly in view of competitive, we are going to have the discussion. So this is what the entire chapter or the unit what we are going to have the discussion. So not all of it within one day we are going to have the conclusion there. It takes some time to complete for all these topics or all these topics to happen. So slowly, one by one, we are going to have the discussion. So today, I am going to start my discussion with laws of motion. You can just make a note of it. Roughly, you can make a note of all the points, whatever it is happening. So firstly, laws of motion. Laws of motion. So I told you already, mainly about Newton's laws, we are going to have the discussion. I am not going to have in-depth definition of the statement of the last Newton's laws, what we are having, all we are already aware of. I am going to make illustrations under that, or the applications under those laws by how we are going to consider. So we are going to have the discussion first, and later on we are going to have some discussion on concepts related to the change in momentum in different cases, how it is, and based on that some applications we are going to have. Based on the change in momentum, we are going to have some applications, we are going to have the discussion on it. So firstly, starting with concept of inertia. Know all about inertia, right? Something which lies within the body itself. The one who is going to experience that will have that within the body. Inertia, what is that? Something resist for the change. Resist for the change within the body. It is going to arise. See, someone is not going to physically apply any force on a body. For example, if you are standing in a bus, for example, and suddenly all of a sudden if the bus starts to move, no one is applying any force on you, but still you will feel like falling backward there. So what is happening over there? No one is pushing you backward, but still you will feel like falling backward. A reason for that. And one more thing, standing in a bus which is moving with uniform speed, and all of a sudden if the brakes have been applied, so what happens? All of a sudden you are going to feel like falling forward. Even here no one is applying any force on you to fall forward. But how come you are going to fall forward there? So once again, I'll give one more example. Like you are sitting in a bus, if the bus is going to have a sudden turn, and suddenly you will feel like falling towards the other end. Instead of sitting in the straight path itself, what you are sitting in the bus, you will feel like you are falling away. In which direction the bus? If bus is going to take the left turn, you will feel like falling towards the right. See what it all is about. Inertia. First thing I mentioned about inertia of rest, and the next thing is all about inertia of motion, and the next thing is about inertia of direction. The 3 points what I have concluded here. Firstly, when you are at rest, if the bus suddenly accelerates, means what? Initially your body is supposed to be at rest. It just tries to be in its state of rest only. It doesn't want to move. It is going to oppose the change of state of rest. So that's what no one is applying any force on it. So that lies within the body who is going to experience that. So that is called inertia, which to say. That's what inertia is. Inertia of rest, which to say. Opposition offered for the change of state. What type of state it is? It is rest, change of state of rest, change of state of motion, change of state of direction. Based on that, 3 types of inertia we are having. Inertia of rest, inertia of motion, inertia of direction. I have given each an example for it. Standing in a bus, all of a sudden bus starts to move is inertia of rest. and if we are sitting in a bus, standing in a bus which is moving with some uniform speed, all of a sudden if the brakes are going to be applied, so then the upper portion of the body it is still trying to continue in its path itself, original path of motion, but the lower portion which are in legs which are in contact with the bus, right, they are trying to stop along with the bus. So then what happens? So there will be, it is going to see the lower portion which is the upper portion which is moving, right, it is just opposing its state of rest. It doesn't want to come to rest there. That's why it continues to move in the forward direction. That's why you'll feel like falling forward. And even the same in case of direction also. That's all about the inertia what we have learned today. So now straight away coming back, the first law gives the concept of force, and the second law gives Newton's second law gives the definition of force, and the third law gives the inference of the force. That's what we are having with theoretically. And theory part we have already studied about all the statements related to the first law, second law and third law. I don't think so again to recall them again. Straight away I will consider with Newton's second law of motion, and what is the relation we are going to write with? F it will be equals to what? Rate of change of momentum we are going to write with. F equals to dp by dt. And here momentum is nothing but what? Momentum is supposed to be written as mass into product of mass and velocity. So how supposed to be written this equation? D by dt of m into v. See, either of these parameters is going to vary with respect to time. Then we'll say that the body is going to be acted upon by certain amount of force. See, it should not be always to be written as F. It should be equals to m into dv by dt. That's supposed to be written as m into a. So make sure that this is not the only valid equation to be written for force. Always to be written is F equals to d by dt of m into v. See, whenever you are going to keep this mass to be constant, when you keep on varying the velocity with respect to time, so obviously in that situation you are going to have acceleration. So then, okay, so instead of that, I am going to have some velocity constant. I just keep a body to have some uniform speed, but mass keeps on varying with respect to time. I'll just give some examples related to that. Even in that case, some force is supposed to be acted on the body. So in which scenario it is going to happen? See, I told velocity, speed is going to be kept constant, where mass is going to be varied with respect to time. F equals to v into dm by dt. See, one best example for this is rocket propulsion. What it is going to happen in case of rocket motion, rocket propulsion or the rocket motion, you know. So like it just completely burns its fuel as the mass of the fuel is going to be burned. At what rate it is going to be burned? Its speed remains constant. At what speed the exhaust gases are going to be there, right? That will be remaining constant. But at the same time, mass of the rocket keeps on changes, which makes some force to be applied on it. It keeps on moving. That's what one point to be remembered. Or one more thing, like one best example you can take is conveyor belt. You might have seen in iron there in or escalator. If you take, even that is nothing but the conveyor belt. See, escalator initially, if no one is there on that, 2 or 3 people have been stepped into the escalator, for example. Even how many number of people are going to be stepped into the escalator, that keeps on moving with the uniform speed itself. Its speed will not be reduced. But what is happening, for every interval of time, dt amount of time, certain amount of mass keeps on adding on to that. So in that case, dm by dt is the mass at which added over during this interval of time. So but you make this uniform speed, that conveyor belt to be moving with uniform speed. So then what happens? Some force you need to apply on it in order to make it to move. That's in that scenario you're going to make use of these relations. In case of what? Variable mass, where speed is going to be kept constant, you're going to make use of the force which it is the force acting upon that body. We're going to have it. So not only in case of keeping the mass constant, varying the velocity, force is going to be acted on a body. Even in case of keeping velocity constant, if mass is going to be varied, then the amount of force acting it will be equals to v into dm by dt. So that is all about one relation you have to remember. So I just want you to remember with both the equations over there, not just with m into a, v into dm by dt also to be remembered. In the future cuts of problems when you are solving, will come about that same thing, so that we'll have the discussion on it. It will be useful, so useful. So when I mentioned force is rate of change of momentum, I told you dp by dt I have mentioned. So what exactly it is? Change in momentum. So how we are going to make it, how we are going to find out this change in momentum in different cases. So very important thing as of for solving the problems in kinematics. Even we are going to have the small related problems on them. or even anyway, how to find out the change in momentum in different scenarios. We are going to have a small discussion. So let me consider, firstly, I'm going to consider a ball of mass m initially moving with some velocity v in positive x direction. Let me consider in positive x direction, ball of mass m is moving with a velocity v, so that initial direction will be equals to, initial momentum will be equals to what? M into v into I cap. That's what the initial momentum of the ball. As it is moving, let's say it is going to hit a wall. It is going to hit a wall so that it just falls dead there itself. After hitting the ball is going to be just like a free falling body. Means just after collision or after it is going to hit the wall, what happens to its final velocity? It is going to become 0. So that's why what will be the change in momentum during this condition means how much it is change in momentum will be equals to final momentum minus initial momentum. So what is final momentum here? 0 minus initial momentum is what? mv into I cap. Hence change in momentum during this case it will be equals to delta p equals to minus mv into I cap. This is what one first condition what you have to remember with how to solve for change in momentum in first scenario. See, in the same problem if I say instead of falling there itself, if this ball of mass m moving with velocity v in positive x direction is going to hit the wall, if it is going to rebound back with same velocity, let me see. If it is going to rebound back with same velocity, then what will be the change in momentum? Rebound back with same velocity means what? Speed will be v, but in moving in opposite direction means minus I cap. So here initial momentum is mv I cap and final momentum is minus mv I cap. Why? Because it is moving in the opposite direction. So now change in momentum will be equals to delta p equals to final momentum minus initial momentum. So what is final momentum here? Minus mv I cap minus initial momentum is what? mv I cap. So finding out the value, so finally you will get delta p equals to minus 2 mv into I cap. This is what about the change in momentum in case of a ball. Whenever a body is going to hit a ball and if the ball is going to rebound back with same velocity, how to find out the change in momentum or what's the relation? Minus 2 mv into I cap. And magnitude of change in momentum, if you want to find how much it is, minus delta p equals to 2 times of mv. That's what change in momentum in case of what? Magnitude of change in momentum in case of a ball is going to hit the wall and if it is going to rebound back with same velocity. So this is about the change in momentum in two scenarios what you have to remember with. So now I hope you got these 2 points. Next, these 2 are simple things. Next, see the same ball which it is going to hit a wall, now not perpendicular to the wall, but it is making certain angle theta with the wall. It is going to hit the wall in this way and it is going to rebound back with same velocity. Let me say this is the normal to the wall I am going to consider. This is the normal. And let's say it is make an angle theta with the wall. This is what the wall is. It is make an angle theta with the wall. This mass is m, velocity v. Rebound back with same velocity v, and once again its mass is what? M. So, same angle theta it is going to make with the wall after rebound. Okay. So now what will be the change in momentum of the wall? Here initial momentum is what? Mu into this particular direction you have to take. And final momentum is what? M into v into this direction you have to consider. So how to find out the change in momentum in this condition? So we will try to solve for it. Important things. So now see this is what the initial direction, right? How much it is mv, and if this angle is theta, this angle also will be equals to what? Theta, right? And what is this component then? mv sin theta, and this component is what? mv cos theta. And once again final momentum, if I want to take this, right? See, I am going to resolve this into 2 components once again. What are those? And this component is what? See, this is theta, means obviously this will be what? mv cos theta, and this is what? mv sin theta. How to write the initial momentum vector now? Initial momentum vector will be equals to, see properly, initial momentum is this, x component into I cap plus y component into minus j cap. You have to write it. X component is what? mv sin theta into I cap. Y component is what? mu cos theta minus j cap. That's why I'll write directly minus mv cos theta into j cap. And now write for final momentum what we got here. This is what the final momentum. This is the x component mv sin theta minus I cap. So I'll write minus mv sin theta into I cap, and even this is vertical component in the downward direction. That's why it is m minus mv cos theta into j cap. So we got these two values now, initial momentum and final momentum we got. So how to find out the change in momentum in this condition now? How to write for the change in momentum? Formula for change in momentum is what? Delta P equals to final momentum minus initial momentum we have to write for. Okay. So just subtract one from the other. So what you'll get? Final momentum minus initial momentum. See, final minus mv sin theta minus mv sin theta will get, this is minus 2 mv sin theta into I cap. Okay, and here minus mv cos theta, minus of minus mv cos theta means plus mv cos, so they will get cancel each other, so you will get 0 over there. So finally you will get change in momentum delta p, it will be equals to minus 2 mv sin theta into I cap. This is the formula what we are having to find out. Change in momentum, if a ball is going to hit the wall and if it is going to rebound back with same velocity, making same angle theta with the wall. See here, ball is making an angle how much? Theta with the wall. Then what is the change in momentum? It will be equals to what? Minus 2 mv sin theta into I cap. What is the magnitude of change in momentum here? Mod delta p, it will be equals to 2 into mv into sin theta. This is what about the magnitude of change in momentum. Now they'll ask even for what is the direction of change in momentum, in which direction this momentum has been changed. The change in momentum is in which direction now? Along the normal to the wall you are supposed to write down. So this is the direction of what? Delta p. Why? Because see 2 mv sin theta is magnitude into minus I cap. Minus I cap means what? In the opposite direction. That's why delta p is in which direction now? Opposite to this direction. This is all about the change in momentum if the ball is going to hit the wall and it is going to rebound back with same velocity, and if it is making an angle theta with the wall, if they are given, this is the condition what you have to write for. This is a very important thing to learn with. The same thing, instead of making an angle theta with the wall, if they are going to mention like if it is making an angle theta with normal to the wall, let's say theta dash it is making with a normal to the wall if I want to mention. If it is theta dash, then this angle will become how much? 90 minus theta dash. Got this point? If this angle is theta dash, then this angle is how much? 90 minus theta dash. So in place of theta, if I substitute for 90 minus theta, what you will get now? So delta p dash, it will be equals to what? Minus 2 mv sin of 90 minus theta into I cap. What is sin 90 minus theta? Cos theta. So that's why it is minus 2 mv, what is that? Minus 2 mv cos theta dash into I cap. So if a ball is going to hit a wall normal to the hit a wall, make an angle normal to the wall if they are given, cos you have to make use. Make an angle with theta with the wall if they are given, sin you have to make use. About these 2 points you have to remember. This is all about the change in momentum in case of a ball is going to hit a wall and how it is going to rebound. So just remember this point. Make a note of this point. Okay, so now like which are all the situations we are going to have. See some more problems on this central conservation of linear momentum. There we will get one few more problems related to the change in momentum, how we need to find out in different cases. So related to that, in center of mass also, like projectiles you are all aware, right? In case of projectiles, if a body is thrown with certain velocity, right? So what is the change in momentum in different cases they will ask. So even one kind of problem what you have to remember. Initial momentum is what? Mu cos theta into I cap plus mu sin theta into j cap. This is what about the initial momentum of the projectile at the point of projection. So at this point with u and theta if it is projected, these are the components u cos theta and u sin theta if you are going to take with. So initial momentum is mu cos theta I cap plus mu sin theta j cap. So now what will be change in momentum of the projectile during its time of ascent they'll ask. So in that case, here what is the momentum when it reaches the maximum height? This is mu cos theta into I cap. Its vertical component is 0 there. That's why final momentum for this journey at this point will be equals to what? Mu cos theta into I cap. So that's why change in momentum for this journey during time of ascent, if they ask, you have to write this mu final momentum is mu cos theta I cap minus initial momentum is this relation mu cos theta I cap minus mu sin theta j cap you have to mention, plus mu sin theta j cap you have to mention. So finally change in momentum during ascent means how much it is? Delta p equals to cos theta term they will get cancelled. Finally it will be equals to minus mu sin theta into j cap. This is what about the change in momentum of the projectile during ascent. So during flight, what is the change in momentum they'll ask? During flight means during this time of flight. So this what? This is the point where it is going to reach the ground with a velocity. We are all aware in kinematics we have learned that. So this is going to hit this with a velocity u, once again make an angle theta. So this component will be u cos theta, and this component is once again same u sin theta itself. See, magnitude of speed with which it is going to hit the ground is same as that at the point of projection. That's why mu cos theta and mu sin theta are the horizontal and vertical components. But how to write that final momentum during this condition, during time of flight means final momentum equals to mu cos theta into I cap minus mu sin theta into j cap. Y minus means its vertical component in the downward direction. So for this, if I want to write change in momentum for during time of flight means, see once again, cos theta term they'll get cancelled. Mu cos theta minus mu cos theta they'll get cancelled. So finally you'll get minus mu sin theta j cap minus, what is this one? Mu sin theta j cap. Mu sin theta j cap. So then what is the change in momentum during this time of flight means minus 2 mu sin theta into j cap. This is what about the change in momentum during time of flight of the projectile. Magnitude if they ask 2 mu sin theta. If they ask direction even, it will be equals to what? Minus 2 mu sin theta into j cap. So the j cap direction also you have to include. This is about the change in momentum in case of the projectile during time of flight. This is all about change in momentum, what you have to remember it. So now, two more points we'll discuss. So how they will ask some numericals or problems related to these change in momentum conditions, where and all they will be useful or helpful. We'll study. We'll have a small point related to that. So now, see, they'll ask the problems like this. I'll just mention a few. See here. There is a wall where bullets are going to be fired from this gun. Let me see. They are going to fire the bullets. Each bullet is of velocity v and mass of m. Bullet of mass m and they have been fired with a speed of v. So now they are going to hit the wall somewhere present here and they are going to stop or get there itself. Let me say. They are going to fall dead there itself after hitting the wall, for example. So now see, whenever you are going to make a bullet to come out of this gun, see, by the conservation of momentum, I have not mentioned it, but still I will just consider that point here. So by the conservation of momentum, see with what momentum this bullet is going to be moving forward, see equal amount of momentum is going to be applied over on it. Means some force you need to apply not to hold this gun. How much force you need to apply not to hold the gun, not to avoid the recoil of it? They'll ask for it. See, they are given even one more point that n number of bullets are going to be fired per second. So that means n is nothing but what? Number of bullets fired per unit interval of time is what n is. So then how to find out the force means, change in momentum divided by time taken for the change in momentum. So here what is the value of delta p? See, delta p how to find out means what will be the change in momentum of this bullet once if it has been hit to this wall, after it is going to rebound back or what it is exactly, accordingly you have to consider. See, and the duration has been taken for a time of t seconds if I want to mention, then it will be equals to delta p value is how much here? If a bullet is going to hit the wall and if it falls there itself, change in momentum we have written it as what? M into v into I cap minus mv I cap we have written, that's why it is mv will be the change in momentum here, and number of bullets hitting per unit time is what? Cap length by t if I am going to write. Then how much amount of force you need to apply not to hold the gun means F it will be equals to n into m into v. This is the point what you have to remember regarding how much force you need to apply on the gun in order to hold the gun. It will be equals to what? Nmv. In the same problem they'll ask like another problem. They'll ask you in the other way like, see the same bullet which is moving with velocity v, whose mass is m. Now, if the bullet is going to rebound back with same velocity after hitting the wall, after hitting the wall, bullet is going to rebound back with same velocity. So, in that condition, so what will be the value of force you need to apply not to hold the gun? They'll ask. Not to hold the gun, what is the amount of force you need to apply? They'll ask for it. So, how to find out that? See here, during the value of change in momentum, can you tell me? Already we have mentioned. If a ball is going to hit the wall and if it is going to rebound back with same velocity, change in momentum will be equals to what? 2 mv. So now n number of bullets are going to be fired per second. That's why it is force you need to apply will be equals to F equals to delta P by delta T will be equals to and delta T value, you know how many number of bullets are emitting per second, we are aware, n into change in momentum is what? 2 mv. That's why force you need to apply not to hold the gun will be equals to what? 2 times of nmv. More force you need to apply not to hold the gun. This is about one more point related to the change in momentum, how you need to apply. So regarding, you just make a note, I'll just mention one more point here. Okay, so now one more point related to the same kind of change in momentum we'll have. So like, based on the same problem, they may ask in different ways of problems like, I'll just mention, see, if a number of bullets are going to be fired into a n number of bullets are fired per second, each of mass m and velocity v, they are given. So now, if they keep on moving like that, somewhere in the mid-air you need to place one metal plate of mass m. So I want to make that metal plate to be at rest in mid-air by firing n number of bullets onto it. So like this, by firing n number of bullets onto it, I just want to make this, no one will hold it, it should be in mid-air just by making that bullet to hit over there. So for that, what is the condition or what is the force you need to apply not to hold the gun in that condition? They are going to ask you. How much force you need to apply not to hold the gun? See here, two conditions again we are going to arise here. One condition is like, after hitting this metal plate, if the bullet is going to fall dead there itself, let me say, means after hitting this, a bullet will come to rest, for example. In that condition, so you know what is the change in momentum for that? Change in momentum will be equals to n into m into v. We are all aware of it. After hitting the wall, if it is going to fall dead there itself, nmv is a relation we are aware. So then, force with which it is going to hit this metal plate will be equals to what? Rate of change of momentum. Sorry, this is delta p by delta t is nothing but nmv. I am written for n here, number of bullets per unit time. So that's why it is delta p by delta t. So in that condition, you see its weight mg will be acting in the downward direction. So what is the condition to be written here is mg should be equals to nmv. This is the condition to be remembered for this particular scenario. See, they may ask for mass. What mass of the metal plate can withhold for this n number of bullets fired each of mass m and velocity v. So then this is the condition. If you tell by giving mass of a metal plate and mass of the bullet, velocity and everything, they may ask how many number of bullets should be fired per second in order to make it to hold there itself. So these are all the conditions what they are going to ask. You see, in the same scenario, if they mention that after hitting this metal plate, if the bullet is going to rebound back with same velocity, you know, if it is rebound back with same velocity means what is the delta p value? You have to mention it as 2 times of mv. Then force with which it is going to hit will be equals to what? 2 times of nmv. So in that case, mg should be equals to what? 2 times of nmv you have to mention. So this is a very important problem. See, I am just mentioning the scenario of the problem how it is. They may ask in n number of ways the same kind of problem. See, all these conditions we are writing for rate of change of momentum. So if you want to find rate of change of momentum, change in momentum in each case, how much it is, we are finding out, and we are just writing for it in terms of the given parameters we are writing. This one kind of problems what you have to remember with. So one more thing, see, like you might have come across few problems related to, see, there will be a hose pipe through which water is gushes out of this pipe with a velocity with the same terminology they will make. Water gushes out of this pipe, hose pipe with a velocity v, and they have mentioned area of cross section of this pipe is A, throughout uniform cross section is A, and density of this water or liquid water which is coming out of the pipe is rho. They have given. Now, you might have seen if water is coming out of the pipe, right, somewhere here they are going to put some collars out there or holders in order to hold the pipe, or else what happens if water comes out of it, just this pipe will move in the opposite direction. So in order not to make it move right, you need to apply some force in order to hold the pipe. Even like if you are going to water your plants, flowering plants or something, when you are holding your pipe, water when it is coming out, so some force is going to be acted upon. It's a conservation of momentum concept only. All these problems are. I am not mentioned, but still I am taking this just to mention about the change in momentum concept here. So some force with some force this is going to be pulled back. So you need to apply not to stay there itself. You need to apply some force on this pipe in order to hold it. How much force you need to apply? They are given this, and they are given one more condition that this water after hitting a wall, it just falls dead there itself. Falls dead there itself means what? It just comes to rest after hitting the wall. If this is the scenario, what force you need to apply in order to hold this pipe there last day? How much force you need to apply? See, they have not mentioned anything about like a time or anything. They have mentioned density of water, area of cross section and velocity. We need to obtain a relation among them for the force here. How to find means, before going for it, so I'll write here mass into velocity. How I am going to rewrite this relation? Mass into, mass is nothing but density into volume. Density is mass by volume. Mass will be equals to what? Density into volume. Volume is nothing but what? A into L. Okay. So into velocity will be equals to what? A length divided by time. Length divided by time. So if I rewrite this relation, force, if you want to write what it is, force will be equals to what? Velocity by time. This is what F, it will be equals to M into A. M into A is nothing but velocity by time. No? So this MV, how I am going to write means rho into AL into L by T. This is what? M into V into 1 by T. Into 1 by T. See, this is, I can write this one as rho into A into, this is nothing but L square by T square. L by T is nothing but velocity, that's why I can write this one as rho A V square. This is nothing but force. Force is nothing but how much it is? Rho into A into V square. So in this, one more term you remember, dm by dt is nothing but what exactly? Rate of change of momentum. How to write in terms of density, area of cross section and velocity of the fluid. In case of fluid mechanics, we are supposed to have this relation, that is. So how to write for dm by dt? Force, how to write means rho A V square, you have written, no? This dm by dt means what? Mass by time, no? Mass by time, how to write means? Mass is nothing but density into volume divided by time. Volume can be written as what? Area into length. Density into area into length divided by time. See, this length by time is nothing but what? Velocity. That's why m by t is going to supposed to be written as rho into A into V. Rho into A into V. So that means dm by dt will be equals to rho AV. Keep this point in mind. dm by dt can be written as rho AV, and V is nothing but what? See, in other terms, in the beginning I mentioned F is nothing but V into dm by dt. Here they are given velocity is kept constant, speed with which the water is coming out is kept constant. So dm by dt value, what we have written there? Rho AV. That's why it is V into rho into A into V. That is nothing but what? Rho AV square is the force with which this water is coming out of the pipe. Same amount of force you need to apply not to hold it. Rho into A into V square. This is about the water which is coming out of the pipe is going to hit the wall, and if it is going to fall dead there itself, what is the force you need to apply in order to hold the pipe? Instead of that, if this water is going to rebound back with same velocity, let me say, if the water is going to rebound back with same velocity, in this condition, what will be the value of force you need to apply? See, with more force water is coming out, so you need to apply the force, more amount of force you need to apply here now. So during this scenario, you know already, change in momentum in such scenario, you have to make it what? 2 times of initial momentum, whatever you got. Here initial momentum we got, it is what? Rho A V square. So that's why change in momentum in that scenario, it will be equals to our force, how much you need to apply in that condition, F dash, if I want to write it, it will be equals to 2 into rho A V square. This is what the force what you need to apply not to hold the pipe. If water is coming out of the pipe and it is going to hit a wall, after hitting the wall, if it is going to rebound back with same velocity, then what is the force you need to apply not to hold the pipe means 2 times of rho A V square. This is what the force what you have to remember. This is what one of the formula which you have to remember with. This is all about the force with which the water is going to be coming out not to hold the pipe. If water is coming out of the pipe, how much force you need to apply not to hold the pipe? This is a condition. See now, one small problem or application we'll see on the same thing, how they are going to ask it. Same scenario I'll take here. Like I'm going to have a pipe like this, and it's going to be clamped at this point. Let me say at this point it is going to be clamped, not to hold it. So now water is coming through this pipe like this, and just it is leaving out of the pipe with uniform speed. With what speed it is entering here, with the same speed it is going to be leaving out from the pipe, let me say. So now no doubt if you're going to leave it like this only, what happens? This just moves away. Some force is going to be acting on it. How much force you need to apply not to place a clamp over here in order to apply this, right? What force you need to, what is the force that is going to be acting on it in order to hold it? They'll ask for it. How much force is going to be acted over here? How much force? F dash or F net, it will be equals to how much? Net force that is acting at this corner of this tube, how much it is going to be? They'll ask for it. How to find? See, particularly this water which is entering here, right, will apply certain amount of force here. How much force they are going to apply? Just now we have studied. They have given the parameters, velocity they have given, area of cross section they have given, and density of the fluid also they have given there. So these three parameters they are given with. Then what is the force it is acting on at this particular end means F, it will be equals to what? F equals to rho into A into V square. F equals to rho A V square. Even if water is coming out of this particular pipe, how much force it is going to be extended on this particular end means how much it is in this direction. F, it will be equals to what? Rho into A into V square once again. These two are the forces which are acting at this particular point. So what is the net force acting in this direction means? F net, it will be equals to these two are perpendicular, then root 2 times of F you have to consider. Root 2 into F. F is how much? Rho A V square. That's why root 2 into rho A V square is the force, what net force that is going to be acted. See, if you won't clamp it, this force make this pipe to move away. So that's why not to make it to stay there itself, not to hold it, how much force that clamp which is going to be fitted here, right, it has to withhold a force of root 2 times of rho A V square. So that's what about this point, this one particular typical numerical which you have to remember. One of the application related to this kind of problems what you have to remember with. So that's what about, just have a make a small note of it.